This video is on the continuation of the first video on critical path method. So in short, we're calling this video CPM 2 because we're continuing from where part 1 ended. So in order to understand this part 2 video, you need to actually start with the first part of CPM first, and then come and watch this one next, because I'm just building from where we ended in the previous part 1. So I want to just redraw the diagram that was there initially in CPM 1. So there was that node 1, which branched off with an A there. Okay, there was a node 2. From node 2 there again we had a 3 below node 3. Then there's a part where we said, okay, so this was actually B. Then there's a part where C and D were like coming to 1. Okay, this will be node 4, and lastly 5 as your node. Should I say, just redraw that for 5. That is your final node. So we had letters like letter C was there, we had D, then there was E. Okay, so one thing we're just going to include on this diagram, which was forgotten in the CPM 1, is that part where there should have been a dummy here. A dummy is just a dotted line which we include on the diagram. So now someone would ask, why including the dummy now? Well, if you recall, go back to CPM 1 video, there was that part which said A precedes C and D, right? Meaning, of course, we have shown it that C and D should not come before A. But the one which was clearly shown was C, because at least we know that, okay, C branched off where A was ending. That's what that means. And then, of course, it was saying where B should become, it precedes C and D, meaning A should come before C and D. But you've noticed where D is branching from, right? It's branching from where B ended because of a certain instruction that was also given. So now that first rule still has to apply to the whole network, that A should still come before D, no matter where it's actually connecting to, in this case, which is from B. So the only way that rule would still hold, because D did not directly branch from A, the only way this would still hold is by creating a dummy. So most of the time we only create a dummy when a certain, should I say, category or letter was supposed to branch from that particular item, but maybe branched off from another route. But in order to keep that precedence rule, the dummy sort of holds that okay, A will still stand before B. So if you can even notice, A is in this region where you know we've written B, meaning after that region, that's when D can come, in short. And that's why the dummy is like demarcating that, okay, you can't come before A, but can come after that. That was one thing which was just forgotten. So then from here, we want to write our diagram, sorry, our figures that were there in the previous diagram. There was a 3, then there was a 1. We actually had a 2. Let me just be sure to clarify those findings as well. Yeah, just a minute so that I can get the right figures as well. So there was a 2 where D is, there was a figure 2. Where C is, there was a 4. And then where you're seeing E, there was a 5, actually, number 5 there. Okay, we now need to create the critical path. If you remember, that video said, okay, part 2 will explain how to create a critical path. One thing you should know is that the critical path is always the longest route. Take this point as gospel truth. The critical path is always the longest route. So let's go first of all through the model that is used to determine the critical path. So what happens is that we start creating, should I say, mini boxes on each node. Like you put a small box there, and you also put like a heart-like shape on the top, right? So what we will be including in these small boxes that will be on each and every node. So like even by node 3 there, we create something like that. You go by node 4, same story there as well. We do the same thing. By node 2, same thing as well. So now, okay, the question is, how are we going to do this? Well, that box, and that box there, then on top we put like a triangular shape. On the box, we'll be putting the earliest starting time, and I'll be explaining as we move. That triangular shape on top, which is like a heart, we'll be putting the latest latest completion time. So these are things that they abbreviate in books as EST, which just stands for earliest start time, and then latest completion time in some books they abbreviate it as LCT. So that's what we'll be just looking for practically. So let's start from the first node and then we'll move just like that. So at node 1, most of the time what you should know is that this is just like from the first beginning there. Nothing has happened yet. No, the network hasn't yet started moving and whatnot. So usually the earliest start time as of node 1 is 0. Just remember that rule. So you have to like squeeze in like a small 0 if you can see that where there's on node 1 in the rectangular box there. Let's just deal with the rectangular boxes first. Let's go to node 2 now. Node 2. Node 2 starts after 1, right? If you've noticed, it's branching from 1. Meaning, there has been 3. If we're looking at days, meaning there's been 3 days for node 2 to come and emerge. Meaning, the earliest start time that node 2 can start is after that 3 days has passed. So you put 3. Make a small box, 3. Okay, just want to indicate this well. Okay, a small 3 there in your rectangular box. Go to 3. On 3 there, what's happening? 3 as well has emerged from node 1, right? And if we can check this, there are actually 2 routes leading to the 3, including the dummy. Yeah, so there's one route coming from 1 direct to 3, and then there's a route from 1, 2, through the dummy to 3. So even that dummy has to be recognized here. So let's check from 1 to 3. There's just been a day, so they've said that one day has passed. Okay, so it could be the possible a day starting time of 3 after a day. Then the thing is, if there are 2 routes leading to one node, take note of this, like in the way this scenario for 3 is right now. If there are 2 routes leading to one node, most of the time, we have to check all the possible routes that are leading to that particular node and then get the largest. That's the rule. So first of all, we determine, okay, from 1 to 3, it's just a day. Let's look at that route from 1, 2, through the dummy to 3. By the way, the capacity of a dummy, I just did not mention this, is 0. Yeah, so let's go through first. From 1 to 2, there is 3 there, right? From 2 through the dummy to 3, there is 0. So it's like 3 plus 0, 3. So you've got a route from 1 to 3, which is giving you just after a day. Then the route from 1, 2 through the dummy to 3 is giving you 3. Which one do you go for? Well, when you're looking at earliest start time, we take the largest of all the routes that are leading to one particular node. So in this case, we'll pick 3, which will go on that small particular rectangular box, and I've put it. Node 4. How do you get to node 4? I'm sure you're seeing what I'm seeing. Node 4 too has got 2 lines that are leading to it, right? There's one route that's passing from 1, 2 to 4. 1, 3, and 4. 2 routes. Check again the same one. When I look at earliest start time and there are 2 routes leading to a particular node, you get the highest of the 2. So let's start with the route from 1, 2 to 4. What figures are there? Well, from 1 to 2 there is a 3. From 2 to 4 there is a 4. This one, let me just put it in brackets for you to identify it. There's a 4 from 2 to 4 there, making a total of 7. Okay, that we just take notes. Let's check the other route. 1 to 3, 3 to 4. There's a total of first 1 plus, okay, there's a 1, of course, but the thing is, we have allocated something first of all node 3, right, which is the only time 3 should start is after 3 days, as we recorded. So usually, in a case where, you've just allocated a certain figure in a box, like in this case, right, you would be picking from the figure in the box there. That's why you should pick to go to like the next node. So from 3 to 4, you already first have a 3 days in the backup first as a startup, and then another extra 2 days. You've seen the route leading from 3 to 4, there's another 2 days. So what I've just done is that I used first of all the 3 which has been allocated as when 3 should start. Now from 3 to 4, you want to know when 4 should also start. So first you start, okay, where 3 has used up its 3 days, then now you lead to 4. So I said 3 plus 2, that route is giving me 5. The earlier route, if you noticed, gave me what? It was like 3 plus 4 gave me 7. We take the higher of the 2 routes leading to 4, which is 7. I even allocate. 7. Okay, go to the last node. From 4 to 5, there's only one route. From 4 leading to 5, there's only one route leading to 5. Therefore, you just add, we start from the number we've just allocated at that node, which is 7, going to the next one. So it's like 7 plus 5 giving you what? 12. So let me just put an arrow for how the node on the, should I say, the structure we've been drawing there will also look on 5. So it should have 12 because 7 plus 5 is 12. After this, what do you do next? Start going in reverse now. You're now going to start with a new criteria of latest completion time. The latest completion time should always start from the last node, which in this case is 5. So you find that, okay, you're on the last node, 5. What would be the latest completion time? Well, again, we said there's nothing else going out from 5. It's like the last point. And they said for 5 to start, it should be 12. And the network also ends on 12. So basically, the latest completion time is usually equal to the earliest starting time. Take note of that. It's always, in fact, it's always equal to the earliest start time. So in that triangular shape now, we're starting to fill in latest completion times. That triangle we've been drawing on top, which is making like a heart shape. So let's put 12 there. A small 12 you've allocated. We're going backwards, as I said. So from 5, what's the next node? 4. We're going backwards. 5 to 4. There was a distance of a 5 there. Let me put in brackets. From 5 to 4, there's a 5 there in brackets. You're seeing it there. There's a distance of 5. So it's like 12 minus 5 will give you the completion time of 4. That's how you read, because we're going backwards. So from 5 to 4, there's a subtraction of 5 days to get you the latest time that 4 should also end. So meaning that's going to be 7 days also. That's the completion time of 4. It's not always that they always match, but depending on this criteria which we're using, like we're going backwards. So like from a certain number to another number, if it appears that the earliest start time and the latest start time, the latest completion time are the same, okay, then we're on good. Yeah, but most of the time the rule is just that on the last node, the earliest start time and latest completion time are always the same. We're on 4. Where next? We can go to 2 or we can go to 3. Let's go to 3 first. So we are on 4 going to 3. There's only one route leading to 3 from 4, right? Coming from 4 this time, going 3 is only one route. Meaning just subtract the number that is along that route, which is a 2. So as of 4, what was your latest completion time? That number in the triangular shape, it's a 7. That's the one we get, because we're now dealing with latest completion time, and it's always found in that triangular shape there. So it's like 7 minus 2, giving us what? 5. That's what we record on 3. I hope you can see that. Let's go to 2 now. How do you go to 2? You can go to 2 through 3 to 2, that Kadami route, or you can go to 2 via 4 to 3, or 4 to 2. That's another route you can get back to 2. So there are 2 possible routes, as I said. Always check. As I said, always check. Or the 2 routes, there are 2 routes leading to a certain node, check. This time around, we are going backwards. So that time when we're coming forward, we're like, if there are 2 routes leading to a certain node, you go for the higher one, which will come out. When you're coming backwards, the criteria changes. If there are 2 routes leading to a node, we get the list of the 2 figures that we'll find. Let's start with the route from 4 to 2. There's on 4, we said the latest, we're looking at latest completion time. That's the one we'll be using. So the latest completion time was 7, leading to 2. In the route there's a 4. So 7 minus 4 gives us what? 3. Okay, that's a possible figure. Let's look at the other route going to. The other route that's going to 2, right? We have a 5. We're on 5 as of 3. We're on 5 as the latest completion time. We're going to 2 now. From 3 to 2, there's in the route there's 0. It's a dummy route we're even using. There's 0. So it's like 5 minus 0, 5. That other route from 4 to 2 gave us what? 3. We said if there are 2 routes leading to another one using the latest completion time, and before stepping backwards, we go for the least, which is a 3. So I'll just draw my weird triangular shape here because of the space on the top, meaning the triangular shape always contains, of course, the latest completion time. So that's a 3, which will go on 2. 5 and 3, the smallest was 3. Let's go to 1. There's a route going, there are 2 routes going to 1. 2 to 1 and 3 to 1. Let's start with 2 to 1. We are using the latest. Don't confuse this one. We're using the latest. So 3, what's in the route? There's a 3 going to 1. It's like 3 minus another 3 there, which gives us 0. Okay, 0 is a possible latest completion time of 1. Let's go to the other root leading to 1. 3 to 1. What's in the root? There's a 1 in the root as you go to 1 from 3. What was your latest completion time as of point 3? It was 5. So it's like 5 minus 1 is 4. This one has given us 4. That root from 2 to 1 gave us 0. Minimum or the least of the two, it's 0. So you allocate 0. So usually when you're coming backwards, we're allocating the least number if there are two roots leading to one particular node. So after this, what next? You can now determine the critical path just after this. How do you do that? The critical path, well, is where those nodes that were having equal earliest start time and equal latest completion time. That's what we just look for. EST is equal to LCT, as I abbreviated earlier on. EST stands for earliest start time, is equal to latest completion time. That's how you determine a critical path. All those nodes that have this criteria, earliest start time equal to latest start time, definitely then you've gotten your critical path. So we'll begin from 1. 1 of course has that criteria already marked. Is there another node? Yes, node 2 has also latest completion time equal to earliest start time. Lastly, look at node 4. Node 4 too satisfies the criteria. It has 7 and 7. They are equal. Last but not the least is node 5. So our route to go from 1, you'll be drawing to my dotted lines. You've watched what I'm doing. That dotted line, okay? Then there's another dotted line passing from 2 to 4. And last but not the least, there should be another dotted line from 4 to 5. That is your critical path. Basically, that's what you do. Then highlight it too. Should I say if it's in the exam, you highlight it that, okay, the critical path now is equal to 1 to 2. I'm writing it on the left side of my screen. Just pay attention there. 1 to 2. Of course, and then 1 to 2 to 5. To 4 to 5. This is the critical path. 1 to 2 to 4 to 5. That's the critical path. That's how you determine it. After that, what next? Get the values that were along that route. From 1 to 2, there was a 3. From 2 to 4, there was a 4, the one in brackets. From 4 to 5, there was a 5. So you're going to say like 3 plus 4 is 7. 4 plus 5 is 7, right? 7 plus 5 is 12. Therefore, the total time that this project can take is 12 days. Because the critical path is what determines how long a project would take. That is the reason why we are determining the critical path. Yeah, and that's just the criteria behind determining a critical path. So now, here's the shortcut. Although it actually uses trial and error, but trust me, you avoid making these to my heart-like shape we've been using in the video. In this, should I say, trial and error shortcut method that we use to determine the critical path, what you just do is that you look at your network, right? How can you move from 1 to 5? Okay, there is a route from 1 to 4 and 5, right? That's a possible route. There's also a route from 1, 3, 4, and 5. That's another route I've seen as well. You have 2 routes. Okay, and then if you want, maybe you might use the dummy route, which is 1, 2, go to 3, 4, and 5. Okay, 3 possible routes going to the end of 5 there. What did we say at the beginning? The critical path is always the longest route in a network. So you have 3 routes as we're trying right now. 1, 2, 4, 5, the one we even selected. It has given us 12. You're adding the numbers along the routes. It's given us 12. Try this other route. 1, 3, 4, 5. There's a 1, there's a 2, and there's a 5. Giving me a total of 8. Remember, we have 12 already. Now 8. Okay. The other one, using the dummy route, there's 1, 2, go to 3, 4, and 5. Let's test out the numbers. 3 plus 0, 3. 3 to 4, there's a 2 there. 5. 4 to that, there's a 5, which is 10. Therefore, we found answers of 12, 10, and 8. Which one came out the largest? Well, it's the route from 1, 2, 4, and 5. So that's just the criteria you can use, and you'll still get the answer right. Of course, yes, it's trial and error, but you are just analyzing all the routes rather than drawing this to my structures we've been drawing here. Otherwise, these tables of these heart-like shapes are just as per standard. Okay, it's one way you can adopt it, or my other, should I say, trick of just handling the critical path method. Okay, so this was part 2 on how you can determine the critical path, and hopefully this will now make sense together with part 1 of CPM. I've noticed in the PET video and the CPM videos that of course when we're drawing those nodes like node 1 going to node 2, we have not been including arrows. Well, it's a requirement in this networking process that when you're drawing a network from one node to another, arrows should be inclusive like that. We just did not include them. It was just for quick calculations and the like, but please, arrows have to be included to show direction of where an event is going and from that point to another. Just take note of this whenever you're drawing any networking model.